All right, good morning. Welcome back to Compilers. Last week we had the midterm. Hopefully everybody did well. We're starting to mark it. We'll try to get it out as soon as possible. Next Monday, we're going to have a lecture dedicated to midterms. If you have certain questions, either join the lecture and ask or send me requests before. Other than that, I'll just pick some of the problems and we'll work through them together. Lab 5 and 6 is out. There's an announcement that we now, since we're done with the midterm, we're going back to the lab sessions on Zoom with the TA. So if you haven't yet finished Lab 5 and 6 and running into issues, do attend those sessions, ask questions. It shouldn't be very hard. The big difficulty is we're using another system, Parboiled. And as any new system, it's a little bit tricky to get started, a little bit tricky to debug. It's supposed to make writing a parser easier for you, but because it generates its own code and it generates code at runtime, if there's bugs in any of this generated code, it's harder to debug since you're not the one who has written it. So it takes a while to get used to it and then benefit from that automation. All right, so today we're going to talk about grammar, and this is going to be the last section on grammar. We'll basically cover everything that we've so far skipped in chapter 4 of the lecture notes. We're going to look into basically how to make grammar LL1 if it is not, and why would we want to do this, what problems we'll see, and how we usually work around them. Okay, so big picture of notes, lecture notes, chapter 4. We talk about engineering design, the KISS principle, so keep it simple as possible. We'll look at ways to specify language, which we already done before, so we'll just run over that quickly. And then we'll focus about refactoring grammars to LL1. And again, it's not that difficult. It's just a bunch of tricks that works in certain cases. It's really like rewriting a program to use one particular idiom without changing its meaning. We'll talk about equivalence, because every time we rewrite, we do change something. It doesn't look exactly how it was before, so something is the same, something is different. And then the intuition for LL1. Okay, so what are engineering design questions? Well, so whenever we look at a problem, we need to know how hard it is. And that's the theoretical understanding of this will tell us what kind of tools we can use. So in our case, we're talking about languages and parsing grammars. So then we need to know how complex it is, what kind of machine we need to accomplish this. And from that, we get to know what kind of techniques are available and pick the easiest technique, right? The one that makes the solution as simple as possible and is good enough. This is what we've learned so far, put together. We have this graph here. As we go up here, complexity increases. The machines get more complex and the languages get more complex, more refined. You always want to be, as close, as simple as possible, depending on whatever task you're doing. At the very bottom here, sorry about this. At the very bottom here, we have regular languages and finite automata, right? So we know regular languages are the ones that we can say specify using regular expressions. They are the kind of things that can be accepted by finite automata. Usually languages where we cannot count or we cannot match, like we cannot match brackets and things like that. Usually this is the languages into which we break our input. So each token is usually something that can be expressed by a regular expression, but not necessarily the sequence of tokens that make up a grammar. So whenever we can, this is what we want to use. If we can solve it with regular expressions, that's what we do. The next level up is what are called context-free languages. And this is languages that can be done with push-down automata. Again, we haven't really covered too much about what a push-down automaton is, but as a computational structure, it's like a finite state machine, except you have a stack. So you can think about it as sort of a program where all variables are Boolean, but you do have functions and you do have recursion. In finite automata, there is no recursion. Here you do. This lets you do things like match parentheses, because every time you see an open parenthesis, you can recurse. Every time you see a closed parenthesis, you return from the recursion, and you make sure that at the end, when you finish reading the whole string, you have nothing on your stack. You're at the base level of the recursion. Now, most of the time, this is sort of the languages that we'll see in computer systems. They will either be context-free or in the space between context-free and regular, so even more restrictive than context-free. We talked about this a little bit, that push-down automaton can be deterministic or non-deterministic. Finite automaton, whether they're deterministic or non-deterministic, doesn't change their expressive power. For push-down automaton, it does. And LL1 was actually, a fragment in here, actually more like this, that corresponds to deterministic push-down automaton. But sometimes we can't have this. Sometimes, so if we're designing our own language, if you want to design some domain-specific language for some purpose, nowadays you would do it together with designing a grammar for it, not just, for example, trying different examples and seeing what looks good, but you'd also write a grammar, and you'd probably try and write an LL1 grammar, and so try and stick inside this bubble. But if you have a language which is given to you, just given to you, and you have to find a way to parse it, then the next level is something called context sensitive, and this is particular kind of automata called linear bounded, and you can look about them in the notes. And if you go all the way up, so here we went all the way up to a Turing machine, and the reason why I'm saying all the way up is because a Turing machine is essentially the most general computational device we have. So any other computational device we have, we always compare that it can be simulated by a Turing machine. And in this case, the languages that we get are something called recursively enumerable. You're usually at this part of the picture if you're taking a class on computational complexity, the theory class in computer science, and you're studying about what is the most things that we can compute, then you're dealing with these languages. In compilers, we are very much in here. And maybe sometimes we stick out a little bit if there is something that doesn't quite fit into any of the grammars, yet we can still, program around it, have something that can recognize it, just not in a sort of well-defined way as a finite automaton or a push-down automaton. Okay, so let's go. Next one. Okay, so in terms of complexity, we also have the time that will require us to parse. So regular languages we parse in a linear time. This is finite automata. LL1, same thing. So basically we do one pass over the input, and we can determine whether this input is in or not in. For context-free languages, in general, we have a cubic algorithm. And then everything else just gets either really expensive or potentially undecidable. So it's useful to sort of have an idea. And again, we've talked about this quite a few times already. It's a good thing to have some idea of what can be that thing that is not regular. How do you know that probably regular language will not work? As a general thing, you would need to prove it using pumping lemma. Again, something that we are not really covering, not covering at all in this class. But there's usually a few things that appear again and again that are so you can spot and be fairly certain that the language is not regular and a grammar is needed. So one is if you have to count, right? So an automaton is a finite automaton. Can only have finite counters, so it can count to a fixed number, but it cannot just count and match the counters. So if you have to accept a string of some number of A's and say the same number of B's, that will not happen with a regular language, with a finite automaton. The very common example of this, especially in programming languages, is balanced parentheses. We often want to have parentheses of various kinds, and they have to be balanced. Every open one has to be followed by a closed one. And that's it. That's something that now requires some memory. The amount of memory is proportional to the size of the input. And so you have to use a machine that has some memory that can grow as it reads more input. And this is where a push-down automaton context-free languages come in. I mean, the same with nested expressions. When you have to go deeper and look for a sub-expression, which is the same as an outer expression, again, you'd need stack to remember how many levels down you went. In terms of our languages, of course, we have a language W, which is regular, and a language F that is not. And again, so if you look at the language, if it's kind of like W, it's probably regular. If it's kind of like F, it probably isn't. There's lots of examples over the years of how if you design a language without thinking about the grammar, you can get into things which are really confusing or ambiguous. There's two examples in here. So one is the hardware description language VHDL. So you have a syntax like this: A open bracket I close bracket. And this is ambiguous because in a language, this could, if you just look at this part by itself, without its context, right? So if you're trying to parse it not in a context-sensitive way, then without a context, you can tell whether it is accessing an ICE element of an array A, or whether it's accessing a function call. And so this kind of things, which are sort of make the language harder to parse, so not LL1 because you need the context. They also eventually make it hard for people to use. So it's harder to then glance at a particular part of a language and know exactly what this thing is doing. Whatever is hard to parse is usually going to make it hard for people to read. So the simpler the language you design, the easier it will be even for people to understand. And then there's this nice example from an airline ticket language. So it's a language for issuing tickets by an airline. It was designed in the 1950s when a lot of these ideas weren't as understood as they are now. And this language is actually Turing complete. What that means, it's a language which is as powerful as any programming language. So you can program in it just like you can program in C or in Java. It's that powerful. And there's absolutely no need for this language to be that complex if all you want to do is do airline tickets. So it's important to keep things as simple as possible. Understand the theory and pick the easiest possible grammar whenever you need one. Okay, so this is a preamble of why we care about these things. So what is a language? Well, I mean, we know what a language is. It's a set of strings. There's different ways to specify it. If it's finite, we can write it all out. There you go. We can just write it all out in this way. We can use, if it's a regular language, we can, of course, write it as a regular expression. If it's context-free language, we can give it a B and F grammar. And if none of those things work, then we can use set comprehension, basically introduce some mathematical symbols to try and describe this language as a collection of things parameterized by some numbers. Right, we've seen this already before. So set comprehension kind of looks like this. We put the set brackets outside. We explain what is in the set, and then we give this predicate that determines what things are in a set. Okay? So for example, this is how we'll say all numbers that satisfy P of X. Here we have all numbers in the range 1 to 100 that are divisible by 2. So all even numbers. And if you've haven't seen this notation in math, you may have seen the same notation in Python instead. So set comprehension is kind of a convenient way to write a set of things where the iteration is inside the set and is implicit. So just a few examples. Let me just get to this point immediately. This is just a slide of different examples of how you specify languages. This is things which are sort of just convenient to remember because the same patterns appear again and again. And if you learn to recognize them, you can quickly see, so if you're looking at the grammar, what it possibly means, or if you have an idea what you want to say as a regular expression but need to go as a grammar, you can write it out. So if we have 0 or more, the pattern is like this. So we say, well, we have the thing that we want. It's either an epsilon, because it's nothing, or it is whatever we want, followed by the same thing. So you could look at this as a tail recursive recognizer. So if you think about how would the recursive descent parser for this look like, well, so you have to decide on this choice. And if the next symbol is x, then you eat x and you recurse on s. And if there is no next symbol, then you say, okay, that's done. S is an epsilon, and we get to the end of input. If we want to do x, y plus, well, that's essentially the same as x, y, y star. And so we just apply the pattern from above. So x, y, y star ends up being this. So x, y, and t will stand for y star. And then now we use the pattern that we saw before. So y star is y followed by t again. And t is possibly nothing, possibly an empty string. Okay. The next pattern is what takes us outside of regular languages. This is why this part is empty. And this is counting two things, basically nested parentheses. We have the same number of x's and y's. They have to match. And then the trick here is that when you do the recursion is in between the two parts. So you're basically saying whatever I'm looking for is either empty, or it is an open bracket, a closed bracket, followed by the same thing in the middle. In this case, I mean, you can have it or not have it. It's not necessary. If you do, this language is not LL1 because we don't know which alternative to pick. But it doesn't change the grammar. The grammar has the same strings in it. Okay. Now, this is where the limit of context-free comes in. So if we happen to want to count three things, so we have not open and closing brackets, but something else and something else, then that we no longer can do with a single stack. And so this language is no longer context-free. You could see figure 4.4 in the notes to see how the grammar for it will look like. And then this is an example of a nested language. Again, it's not regular. And here we really care about the parse tree. And so the parse tree that we get is we have a start, which is an expression. An expression is an expression minus something else or something else. And then this something else can either be some basic thing, like an integer in this case, or it's an expression itself, but now it's surrounded by brackets, right? So that's the nested part. Okay, and we'll see more examples like this, and really you've seen the F language. There's a lot of examples of this kind. And really, for the most part, whenever you're building a new domain-specific language or trying to come up with a grammar for an existing language, most likely it's going to be some combination of those things. There really isn't all that many different patterns just because, we're used to certain kind of languages and we keep reusing the same patterns, changing them slightly, but mostly keeping the same things because that's what is simpler and easier, since that's what we are familiar with. All right, so next step is, say we have a grammar, and it is not LL1. And so the question is, can we turn it into LL1? This is what we're going to cover now. And the first question is why? Well, there are several reasons. So why do we want to refactor a grammar that is not LL1 into LL1? Well, the first question to ask is, where does the grammar come from? So if you're coming up with your own grammar, That is, for some reason, you need to create a domain-specific language. None of the existing languages that are there are good enough for whatever you're doing. Then you probably want to make sure that the language itself is LL1 to begin with, because it's the easiest one to parse. It can be parsed top-down by a deterministic mechanism. The only thing that you need is stack or recursion, which means that the language will always be easy to understand. Anybody who's looking at something in your language, they can run the same algorithm in their head, just look from top down, and they can immediately see what's happening at every point, basically doing recursive descent parsing in their head. If you do something more elaborate, then the language may be interesting, theoretically more esoteric, but it will be harder to parse because you will need to use the context in order to understand what's going on. And usually that's not a good thing. You have to have a really good reason why you want to complicate it that much. So now that you have the language that is LL1, or at least you hope that it is, you can try and write a grammar for it. Or perhaps somebody's given you language and maybe even given you a grammar that they believe this language is that covers this language. It's possible that the grammar itself that you're going to get, at least initially, just by trying to formalize what you're interested in, the grammar itself may not be LL1. Right? Remember, we've talked about this a few lectures ago, that we have a language, the set of strings. That language is LL1 if essentially we can parse it using recursive descent. And then a grammar is LL1 if, whenever we automatically compute a recursive descent parser for it, we will always succeed. That is, when we compute our predict sets, they will be disjoint. And so it's possible that we have a language that is LL1, so in principle easy to understand, but the grammar that isn't. The grammar is more complicated in some way than what it really should be. And this is where it's useful to know some basic refactoring patterns, because it's possible that the language is very close, or the grammar is very close to LL1, and with a few fixes you can just get it to be that way, as opposed to saying, oh, looks like something is wrong in my grammar, let me start again from scratch and try and guess somehow how to make it LL1. Now, the second question is, what is refactoring? Okay. And so here we have, again, two things. So refactoring that we're going to cover in here is how to get the grammar that accepts exactly the same language but is LL1. So it's just like refactoring in programming. We're going to rewrite the grammar in such a way that it means exactly the same thing, but it now fits into LL1. Of course, if you do this in practice, again, you have these two choices. Sometimes you're creating a new language, sometimes you're creating a grammar for an existing one. If you're doing it for an existing one, you don't have a choice. You have to use refactoring like this. If you're creating a new one, and if you discover that, I've made some decisions and they contradict one another and it's not LL1, then you want to not refactor the grammar, but rather change the language so that it becomes LL1. But here we're assuming somebody's given you the grammar. You don't need to do your own design. You just need somebody's given you the language, and you just need to do the grammar. Okay, so this gives us a question about what does it mean for things to be the same, right? And again, we've talked about that also before. How can we compare grammars? And so we have two ways to do it. The grammars can be strongly equivalent or weakly equivalent. So strongly, in both cases, the grammars are equivalent, meaning that they represent exactly the same language. Right? So what we accept and what we reject is the same. And grammars are strongly equivalent if also the abstract syntax trees are exactly the same, and they're weakly equivalent if the abstract syntax trees are different. So how we parse things could be different, the parse trees could be different, then the grammars are weakly equivalent. Otherwise, they're strongly equivalent. The kind of refactoring that we're going to do here, they will mostly focus on weakly equivalent, because that's actually how we're going to turn the language to be LL1. The way things will be parsed will be different. We'll see this in a bit. Okay, so let's look at the things that we're gonna look at. So we're gonna look at what to do about common prefixes, then what to do about grammars that specify it using left recursion. And this is really where the ASTs will be different, the left recursion versus right recursion. And then we're gonna look at ambiguity, which is where the grammar is not LL1 because it can parse the same input string in different ways. And we'd like to only have one way to parse each string. Okay, so the common prefixes. This is an example. So say I have a part of my language, I have a grammar that looks like the one over here. Okay. And so here I'm gonna stop and ask a question and wait for you to answer. Is this grammar LL1? And if it is not LL1, why is it not LL1? So this one is easy. It is not LL1. Okay, somebody said left recursion. That's not the case. It's not LL1 because both of the things start with an ID token. So if I compute my predict sets, it's definitely going to be that the predict set for the first rule has ID and predict for the second one has ID. Okay? It's not left recursion because even if ID is not a token, but is some kind of non-terminal, it's not a recursion because this is statement and this is ID. Well, how can we fix this? How can we make this LL1? Any idea? Well, essentially, what we want to do is we want to make this choice and put it in here instead of between these two complete rules. So the trick is to move this disjunction further in. And we can do this by introducing, just by refactoring it the way that you see in the picture and introducing a new non-terminal. So we'll say statement is ID followed by some t, and t is either equal expr or bracket expr bracket. So now here we have a choice, and the choice is different because, sorry for this disappearing. Let me go to this example now. Okay, so this is the same thing, but now on a slide rather than me writing it. So we introduced a new thing called t, and now the choice, this choice, is definitely LL1 because the predict will be different. This one will have an equality, and this will, sorry, this choice is different. So this one will have an equality, and this one will have an open bracket. And here we no longer have a choice, so we don't need to worry about even what the predict set is. Now this should be very obvious for you, that in any point, whenever we have any kind of a rule, we can always pick a part, introduce a non-terminal for it, and factor it out. And so this way, we can move this choice later until a point where it can be made based on the next symbol. Now, you can just remember this example. And from this example, you can always reconstruct what the general case is, or you can remember the general case. So here's the general case to do this transformation. If I have a prefix followed by a suffix and another prefix followed by a suffix, and the prefix is the same, and this is part of one rule, then all I have to do is factor out the prefix out, introduce a new non-terminal, and make the choice based on the suffixes. If those suffixes have something in common again, I can do it again, introduce another tail, and so on and so on. It's very clear that this is very mechanical. You could show that this procedure will always terminate, because each time we make rules with smaller and smaller body, it will at least remove this kind of ambiguity, eventually getting to a point where you cannot do anymore. And so clearly you can even have an algorithm that does this. And there are algorithms like this. We're not studying them because just for our purposes, it's enough if we can do it by hand. And a fancy parser generator may do this for you. So it will allow you to specify things which don't quite look like LL1, as long as they can have an algorithm to convert it into this simpler form. Okay. So next one is left recursion. So this one is trickier. So let's first look at the grammar, the language, and then think about what to do. So the grammar that we have here is this one. And let me switch so that I can write and my annotations will not disappear. So this is our language. If we think about what's in this language, if we do a few derivations, we'll see that, okay, ID is in this language. ID, comma, ID is in this language. ID, comma, ID, comma, ID is in this language. Right? And if you think a bit more, really this is the language of ID plus. Okay. If it's a language of ID plus, we can immediately think about what the solution would be, because we can represent ID plus in LL1. But before going there, let's think about what's the problem with this particular way. So the problem here is that we have this recursion saying go and if you're processing a list, go and recurse and see if there's sort of a bigger element of a list. The problem is that the recursion happens first before we make any other choices. So we come to this choice between this rule and this rule. And we don't know what to do because we have to either call list recursively or we're supposed to be at the end. And if we only have one look ahead, we can't really tell. If we recurse, well, as we recurse, we come back to the beginning of this rule and we have to recurse again and again and again and again and again. And there's no way for us to know when to stop recursing if we only have a one token look ahead. So if we write, for example, a recursive descent parser for it, just following the methodologies that we have, then we'll introduce an infinite recursion, an infinite loop in our parser, and it will never be able to terminate. But of course, the only reason why we have this this looping construct is to just do something many times. This is just recursion, a looping. And so we should be able to rewrite this so that the recursion is, rather than left recursive, becomes right recursive or tail recursive. That is, that we do as much as possible first and recurse only at the end. And again, we can just see at this example, this is the language that we're trying to understand, ID plus. And so we can just come up with a grammar for this and then compare the two. So let's see what we get for ID plus. So we say a list is what? Well, it's either an ID, then a comma, and so let's see. So if we want to do an ID plus, it's actually more than ID plus. Let's fix this a bit, because I'm forgetting about a comma. So this is actually an ID, comma, ID star. So list is ID, comma, ID star. And we know how to do comma ID star already. So we say, let's introduce a new terminal for this. Let's call it T. And T will go to either comma, ID followed by T, or epsilon. Right. So this one is right recursive. It accepts exactly the same language as the one on the left. So the language is ID followed by comma ID star. The parse tree will be different. Here the parse tree will sort of grow to the left, and here the parse tree will grow to the right. It's just so how we just accept this repetition, but only the same strings will be accepted. So these two grammars are weakly equivalent because they accept the same language, but not strongly equivalent because they parse them differently. Let's see what we have on the slide. So on the slide, the solution is exactly the same. Right, and again, you can either sort of memorize this kind of solution once, or it's quite easy to derive once you understand the language. Right? So once we know how to represent a star with tail recursion, then all we had to do is just figure out that this is what this language is. Again, the language is ID, comma, ID, and this tail can appear 0 or more times. Again, so you can either remember it on one example and just see the similarity and apply that same thing, or you can remember the general pattern, which is here at the top. So if we have something which is left recursive, where a goal appears in a rule and also in the beginning of the body of a rule, then we can convert it into tail recursive or right recursive this way, right? Where we say, well, it's either a prefix, which is usually here, followed by everything else 0 more times. So tail represents suffix 0 more times, and 0 more times is represented this way. It's either 0 times or it's 1 followed by 0 more times. Now, I don't know how to give you more intuition in how to do this refactoring. So we saw these patterns, and if you play enough with these grammars, it really becomes kind of like programming. So you've written a program and you're trying to restructure it a bit. And so in this case, for example, we introduce a function in the middle so that we have, rather than two choices, we have one choice followed by a function, and then we push the choice inside that function. And here we really just think about what we want to compute, and we change this computation to be tail recursive using tricks of how do we represent something how do we represent essentially a star using a tail recursive thing. It's not very hard. It may look mysterious at first, especially because grammars tend to be mysterious. But once you sort of play with them enough and you understand that really all that it is just a kind of a programming language, and I'm just rewriting the program to be more towards how I like them to be, then these things become quite easy. You don't really need to remember like in details, all of those patterns, they're quite easy to reconstruct from simple examples. Okay. So don't see any questions yet. So the next step is ambiguity. Ambiguity means that the same string can be parsed in multiple ways. That is, we can create multiple parse trees from the same string. Or that means that we can have two different derivations on the same grammar that end up in the same string. Now, there's always examples from natural languages. So, for example, if we say something like a Canadian history professor, right? So we have a question, is that a history professor that is Canadian? Or is that a professor of Canadian history, right? So we have, we don't know how to interpret, and the actual interpretation may depend on context or on other information that's not even in the text that we're trying to parse. And for this reason, from the linguistic perspective, there's a desire to be able to represent this formally, mathematically. And so the grammars support this for that reason. But for a programming language, we actually never want this. We want everything to be as simple as possible, to have just one meaning and just use basically more words if we want to have different meanings. So the grammars allow ambiguity, and they allow ambiguity actually on purpose. That's a plus, that you can express things that happen in a natural language. But whenever we use a grammar to design a programming language, we always want to make sure that it is not ambiguous, that there's only one way to do it. So where do we have, what is the source of ambiguity? Is, of course, the choice, the bar. Not every bar causes an ambiguity, but every ambiguity is caused by that bar. And so, we'd like to have languages without ambiguity, right? And in particular, we're using this PEG languages in our last lab, and the PEG expression grammar is exactly a grammar that just removes all possible ambiguity. It's just not even possible to describe an ambiguity in that grammar. So in a normal grammar, the ambiguity comes from a bar. So let's look at this example. So say we say S is either an A or a B, and A is an X and B is an X, which means a string containing X can be parsed in two ways. This is 1, this is 2. So this grammar is ambiguous because whenever we want to build a parse tree for X, we can't build one uniquely. And that means when we're parsing, say if this is some programming language, well, if the user just has X as an input, we don't know whether they meant an A or whether they meant a B. One way to get rid of this, well, there's two ways to deal with this problem. One, and we'll look at this a little bit in the following slides, is just don't allow this in a grammar. So for example, if you have X and you want either A or B be X, just change your grammar. Say remove this and somehow deal with the fact that you only have an A now and not a B. And if you need to guess that, sometimes X is a B, do it somewhere else outside of the grammar. Right? So you can fix ambiguity by changing the grammar. An alternative way, and this is what is called PEG grammars. The reason why we talk about them, because this is a grammar that parboiled supports. Also, we're not really using that feature, but it's just a good idea to know what's going on in there. In this language, in these grammars, the choice, the bar, is replaced instead by a choice called first of. And this choice says that it's not that either one of the alternative match, but really the order is important. And if the first alternative matches, then that's the alternative to go. So here, for example, there's only one way to derive X. because if we have an x, then this can be made true, and therefore that's the only thing that is made true. A way to think about it, maybe that's more concrete, is that if we build a recursive descent parser for this grammar, and we compute our predict sets, but we won't care whether they're disjoint or not. And instead, we'll just write our parser and we'll say if, so inspect x, then a, and then else, and then we put the same predict set, but it is on the else branch, b. Okay. Then this is what a peg grammar, that's how peg grammar interprets a choice. It says first do the first one, and only if the first one fails, then do the else part. Okay. So then in this case, even if our predict sets are not disjoint, the ambiguity is resolved because we're always picking the first one. That means that the order in which we put things becomes important, but it's kind of how we program anyways, and so it's very convenient. And so this gives us a different way to express our grammars, where this choice, the bar, which is nice to capture ambiguity in natural languages, is replaced with first of, which closer corresponds to sort of what we would want programmatically. This gives a really interesting theory of those languages, because then the grammars that we can capture, they're not quite context sensitive. They can capture a bit more than that, and they're not quite all of context sensitive. But it's kind of, from the practical perspective, it's an extension of LL1 that makes it easier to work with a grammar. You no longer need to worry about whether your grammar is LL1 or not. You just say, whenever there is an ambiguity, I always pick the first choice. And I just have to be careful to decide what choice is first. Now, you won't really run into any of this during the labs. The only place where you're going to run into it is that you have to use first of for the choice. But because our grammars are LL1, it really means that all of those conditions for different inspects will be disjoint. And so the fact that there's an else clause doesn't really do much. Okay, so where does ambiguity come from in practice? What's the most common place? And the most common one is associativity. Right. So we have this operations where we don't want to use. Well, we have this fragments where, like here, where we don't want to use brackets when we write this. And if we don't use brackets, it looks like it can be parsed in both ways. And usually we have one particular way in which we want it to be parsed. And so this is where the ambiguity comes, and where the ambiguity is not something that we want. So for example, for subtraction, we'd like it to be parsed this way, right? So we'd like to get a parse tree that looks like this. As opposed to the other way around, because this is how the associativity of negation works. The way we deal with this is we refactor the grammar to be unambiguous. And again, most of the time, it's really just sort of this kind of things, that certain operations tend. So associativity is one, and then we need to refactor the grammar to deal with this. And the second one is operator precedence, right? So if we have x times y plus z, which way do we want to parse it? There's two different ways to parse it, and we only need one. And out of this two things, the precedence, that there's different operators, and associativity, that's the same operator many times, and the parse tree has to be done one way or another. That's the two most common ways to do it, two most common problems that appear again and again. And again, the way to deal with them is you just look at the patterns, like what we have in our F language, and you just learn to recognize the pattern in there and just replicate the same pattern whenever you add more operations. So all that we have in the following slides is just a few examples like this. Most of them will be way too quick to present now. So I'll sort of scroll through them, but really they're here so that you can go back whenever you ever faced with a problem of, ooh, I need to deal with operator precedence or associativity, and you see what sort of the template is, and then the same solution will just work. Okay, so ambiguous associativity, this is addition. This is what I was drawing with negation before. So if I have a grammar like this that says the grammar is an expression or an expression plus expression, where or an expression is an integer, so it will match strings like this, but it can match the strings in different ways. Whether we first recurse on this, or whether we first recurse on this, right? So here's one derivation where we go and expand the leftmost thing. And here's another derivation where we recurse on the rightmost thing. This will give us a parse tree plus 3 plus 1, 2. And this will give us a parse tree like this. So this grammar is ambiguous. That means if our goal is to build a parse tree given a string, so we're given this string and we're trying to build an AST, we can't really use this grammar because there's 2 ways to go and we don't know which way we need to do it. So how do we fix it? Well, see, we can fix it by sort of going for either this parse tree or the other one. So basically by not allowing both recursions in here. And so we have 2 solutions. This one is called left recursive because the symbol that is recursive is leftmost of the body of the rule. And this one is called right recursive because the symbol that we recurse on is on the rightmost symbol of the rule. Right associativity gives you this parse tree. Left associativity gives you this parse tree. Okay. So what does that mean? It means that whenever we have something with ambiguous associativity, well, we get to either make the grammar left recursive or right recursive, and then the ambiguity goes away. If we also want the language to be LL1, then we pick right recursion because left recursion is not LL1. Any questions? There is a hidden question in here. But it's usually not that easy to get when you just see it the first time. Yeah. So again, just to summarize the solution, is if you have problems with associativity, that is, you have a grammar like this where you recurse both left and right, E plus E, then the way to fix it is either you say it's E plus something lower in the grammar, so in this case it's int, or it's int, or it's something lower in the grammar plus E for the right. The choice between left and right, both of them will fix ambiguity, so you can use either one. And if you also want your result to be LL1, then you have to stick to right ambiguity. And so there is a question. So, okay, this is nice for addition, because for addition, we don't care whether it's left associate or right associate, if it's exactly the same thing. But if we were to change this to negation, use a different color. So what if we change this to negation? And then everywhere here we have negation now. Yeah, my drawing skills are not very good. Okay. So if we put negation everywhere in here. Right. Then we're going to have a problem because this is the one, this is the correct one. And then it has to be left associative. So if we have an operator which is left associative, and we want to fix this ambiguity, then we cannot possibly fix it by using right associativity, right? While staying in LL1. And there is a solution to this in a couple of slides, but like I want you to be aware of this question. We're going to see the solution in a bit, but that's a question that you should be having. So, okay, it's easy. If the operators are not associative, if we can do them either way, then always just associate them to the right. But if they are left associative, we have to do something special. And one something special that we can do is make the grammar not associative at all, and then fix the AST construction later on. But again, easier when we see it on the slide. Now, the next thing is operator precedence. Okay? This guy. And so here again, here's an example of an ambiguous grammar where we say an expression is either a plus or a multiplication. This is also, to me, more fun, is made left recursive here and right recursive here. And then, of course, it's going to be ambiguous because if we're saying we have one operator and another operator and they're in the same level of the rule, then it's not clear which one we need to do first. And the solution is what we saw in an F language, is that we build an order of operators, the precedence, and we have terminals for non-terminals, capturing lower levels, appearing lower in the grammar. So the higher the precedence, the lower the non-terminal comes. Right. So something like this. So we've introduced here this extra f, and f takes care of multiplication. So essentially what we're saying is that instead of saying it's addition and multiplication, we're saying the way we recognize the grammar is you can have as many multiplications come together as possible, followed by a plus. And then after a plus, you do it again. Either it's as many multiplications as possible, followed by another plus. If you look at this, right, this itself is really like saying that we're doing an int followed by a star. Well, it's left recursive, so it's not quite that, but the pattern here that we're capturing is int followed by a star. Right? This is what f is. So we're taking all of the multiplications together, and then we have a plus, and then we repeat. Okay. So again, the way you remember this is that what you do is you introduce, you break your operators so that each one has its own non-terminal, and the lower you are, the higher precedence you have, the tighter you bind. Okay, so this should summarize what I said. So each level of precedence is its own non-terminal. The lowest level is the top level. The lowest level is higher up. So whatever binds less tight is at the top of the production. Each production uses the next highest level of precedence. And highest level of precedence includes the operands. Right? So we have S is an expression. And an expression is, well, something that binds tighter than the operator, and then the expression again. So this is because we want it to be left recursive. And then it's possible that we don't have this operator, so f itself is also in E. And then the same thing here, where now int is a slower level. Right? So int here is the same as f in here. Again, it's hard to give you more intuition other than saying just look at a couple of examples look at the rules for the basic arithmetic for addition and multiplication, and then just follow the same pattern. Yeah. So okay. If there's no questions, there's one other thing that sort of is always shown at this kind of class, which is the problem of a dangling else. So this is a common problem in any language that is derived from C, which is given the string, how do you interpret it? So what is the actual meaning of it? There is an if statement outside here. There's another if statement in here, and there's this else. And so the question is this else for this if, or this else for this if? And you can't really tell from this. And if we look, so this is the two examples that I was showing, whether this else belongs to the inner if, or whether this else belongs to the outer if. And if we look at the grammar, this is, what is the source of that problem? That the grammar says a statement could be a conditional, and a conditional is an if with a condition followed by a statement, or it's an if followed by a condition, a statement, else, and a statement. Okay? And so we have two choices. Whenever we see an else outside, this else could be part of this if we parse it that way, or it's possible that the else is part, that the whole if else itself is a statement because it is a conditional, and then the outer if is parsed using this rule. And this is sort of a very known form of ambiguity that sneaked into the C language, and from the C language it's been replicated in lots of other languages which derive themselves from C. Now, how do we deal with this in practice? Well, it depends so whether you have a control, you're designing a new language, or whether you're stuck with the language because it's already there. So in lots of languages, you also have an and if marker. So either an and if marker, or for example, you always have to use the braces so you don't get the form without braces. In some languages, every if has to have an else, even if it's blank. So this is Haskell as an example. In Python, the decision was made is to just use indentations for everything. And so you have to put your else in a particular indentation. Otherwise, in languages like C and then languages that derives from it, there's just an explanation somewhere outside of a grammar that says only the parsing where the else attaches to the inner if is the legal one. And then whoever is writing the parser for this grammar has to figure out how to make it work. So they won't be able to use any of the standard parser generating techniques. They'll have to tweak the parser a little bit. If you're interested, there's a story of sort of where this has originated. So it came from Algol 60 and then spread to lots of other languages that took inspiration from it, took some of the syntax and sort of imported the dangling else problem. Okay, so we have done this. This is a part that I wanted to also cover that I asked about, is that what do we do with LL1 grammars and left associativity? So this is the thing that I alluded to, that if we have, say, negation and we want to make it unambiguous, then we have to make it right recursive. But if we make it right recursive, it's also right associative, but negation is left associative. And so the solution is, what we do is, instead of this, we basically parse it as right associative, and then we fix it as we construct an AST. And so this is how it would look like. So you would basically parsing it using this EBNF pattern, right? So you have an int followed by negation and int and as many of them as possible. Now you will expand the star into something which is right recursive, so that this becomes LL1. But then what happens is that whenever you process another negation, when you construct the AST, you construct it to be left associative. Even so, you know that if you just follow the grammar, it would have been right associative. And this is sort of the way we usually get out of this kind of problems. So we have this formal grammars. We have an ability to generate a parser automatically as long as we completely fit into the grammar. And if we don't, we can often find a solution by just adding a bit of extra code so that the parser that we get is not completely automatically generated. So usually the AST construction is not quite automated because we have to make some choices which sort of cannot be expressed by the grammar. And so we express them ourselves by sort of saying, oh, I do the normal parsing, but I take over, say, at this part, and maybe I change associativity the way I want, rather than the way it comes naturally in the grammar. Okay, so then how do we design the grammar? Again, this is just an example for you to look at. I'm not going to cover much of it. This is the only two things that sort of come again and again and could be tricky, which is precedence and associativity. And all you have to do is just remember one example of a simple language. The one you already work with is F, so might as well remember that. And everything else that you're going to ever face will be a variant of this. You can have different operators, you can have more operators, more hierarchy in precedence, but it's all going to be the same. And you have associativity left and right, and so you always convert it into right, and then transfer the AST to left associative when necessary, if that's what's needed. So here's an example. So again, as I said, I'm not going to go over it, but this is just an example for you here that, say you want to have addition and multiplication. This is 2 levels. So you pick the right associativity. This is how it looks like as EBNF, which is a little bit more readable. And then to refactor it to LL1, all you have to do is model the stars properly, which is by adding this tail non-terminal. And that's it. Here's a grammar for subtraction and power. Again, same thing. And an example with nested sub-expressions. Again, the only trick here for nested sub-expressions is you want to have something so that you know what kind of recursion you're having and why, right? So we have brackets so that can indicate, oh, it's a different thing, and now I know I'm looking for an expression and then a closing bracket. Right? And so this is basically the patterns that cover almost all use cases: nested, and then left and right precedence, and when associativity does not matter. So if you can build grammars for each one of these cases, and if you can write the recursive descent parser for each one of this, then it basically covers almost everything that you'll ever going to see. That's it. That's the end of the lecture. That's the end of grammars. So from this point on, we're going to go into what happens after we've parsed. What are the next stages of compilation? That's it. So if you have questions, ask now. If not, but you have them later, ask them on CampusWare. And then I'll see you again on Friday. And Friday, we're going to go back to our labs and we're going to talk about lab 7. All right, I don't see any questions. So that is the end of the lecture. See you Friday.